Hello students. So today we are going to discuss more about voids. Okay. So you know we have different types of voids. Which are they? Tetrahedral voids, octahedral voids, cuboidal voids, etc. So all the things we already discussed in our earlier classes, right? Now I am going to discuss how to locate these tetrahedral voids and octahedral voids. Okay. So we already learned that in CCP structure we have 8 number of tetrahedral voids and 6 number of octahedral voids, that also you know in CCP packing. Okay, so how to locate these tetrahedral voids, that we will discuss. Okay, so first one, tetrahedral, how to locate the tetrahedral void in CCP structure. That means CCP means that is same as FCC, unit cell is FCC here. Okay, so in FCC unit cell, you know, particles are present all the corners and also all the face centers. Okay, so we have six faces here and particles present at all the corners. Okay. Okay, so now you have to divide this unit cell into 8 small cubes. You have to consider this single cube into 8 small cubes. While taking this small 8 cubes, one of the cube I taken outside from the. So we first of all we have to divide this big cube into small 8 cubes. By dividing this, we can see that small cube consists of particles in alternate corners. Okay, so you know for a cube we have 8 corners. So in the small cube I told you particles are there in the alternate corners. So how many particles will be there? 4 particles. 4 particles are present at the alternate corners. So when you join these 4 particles, you will get a structure like a tetrahedron. So that is the tetrahedral void. Okay, so I told you we divided that big cube into 8 small cubes. Each cube have a 1 tetrahedral void. That means how many number of tetrahedral voids that have? That is total 8 tetrahedral voids have for a CCP structure. Okay, so you know in FCC unit cell we already discussed the number of particles per unit cell. How much? You know 8 corners, 8 into 1 by 8, that is equal to 1, and also all the face center we have 6 face center and each face shared by half of the particle. So 6 into 1 by 2, 3. So total number of particle is equal to 4. And here you see that total number of tetrahedral void is equal to 8. So that means tetrahedral void is twice as that of the number of the particles. So that's all about the locating the tetrahedral void. First of all, you have to consider 8 small cubes and each cube has a 1 tetrahedral void. So here you have a total of 8 tetrahedral voids in CCP structure. Now look at the octahedral void. What about this? So same the structure you consider CCP or FCC unit cell. Okay. So in CCP or FCC unit cell, you know that there is no particle in the body center, isn't it? Yes. Okay, so here the body center there is no particle, but body center is covered with a 6 particle of the face center. So body center particle illengilum, this which is surrounded by a 6 particle of the 6 faces. So there is a chance for formation. While drawing this 6 particle together, we will get a structure of octahedron. Okay. So by joining this particle we will get a structure of octahedron. That means in the body center we have one octahedral void. Okay. So besides this, besides this we have in edge center, we have for a cube how much edges we have? Yes, 12 edges we have. So in the 12 edge center you have a, we do not have a particle here, but in the 12 edge center we have a 6 spheres surrounded by it. Which is the 6 spheres? 4 from the same unit cell and 2 from the other unit cell. Like that each edge center is surrounded by 6 spheres. So there is a possibility of forming a octahedral void. So each edges there is a possibility of forming a octahedral voids. But you know that in edges anything is formed, you know, edges where particle is present, that means എല്ലാ പാർട്ടിക്കിൾസും ഈ ഒരു യൂണിറ്റ് സെല്ലിനല്ല, only 1/4 of the particle കിട്ടുള്ളൂ. Like the same way, if any octahedral void is present in the edge center, we will get, for a single unit cell, we will get only 1/4 of the octahedral only. Okay, so how many number of octahedral void for total unit cell? We know we have 12 edges, and each edge share 1/4 of the octahedral void. Okay, so 12 into 1/4, that is equal to 3. So total number of octahedral void is equal to 1 plus 3, that is equal to 4. Total number of octahedral void is equal to 4. So you can see that here FCC structure, the number of particles per unit cell is what? 4. So here the number of particles per unit cell is equal to the number of octahedral void. But what about the tetrahedral? Here the number of the tetrahedral void, number of tetrahedral void is equal to the twice of the particles, isn't it? So that is all about the octahedral void location and tetrahedral void location and octahedral void location. Okay, next we will calculate the density of the unit cell. So why we calculating the density of the unit cell? Okay, knowing the density, we can calculate the number of parameters using this equation. Okay, we know from the unit cell dimension itself we can calculate the volume, or also from density, you know what is the equation for density? Mass by volume. So you will get the mass. From the mass you can calculate the Avogadro parameter accurately. We already know the value of Avogadro constant, but from the mass itself, from using this equation we can calculate the accurate value of Avogadro constant also. How we will calculate this density? So you know, the volume of the unit cell is given by the equation A cube, where A is the edge length. What is edge length? The length of the sides. So for a cube, all the sides have equal length. So volume V is equal to A cube. And you know, density is given by what? Density is given by mass of the unit cell divided by volume of the unit cell. Okay, volume we already know, that is A cube. How will you find out the mass of the unit cell? The total mass of the unit cell is given by is equal to number of particles present in unit cell into mass of the each particle. Okay, suppose Z is the number of the particle Z, and the mass of each unit cell is M. Then the mass is given by Zm. Okay, and mass of the particle in gramil nammal edukkumbo divided by Avogadro number. So that is equal to Zm by Na. Okay, so you know what is the density of the unit cell? Mass of unit cell divided by volume of the unit cell. Here mass is equal to Zm by Na, where Z is the number of particles per unit cell. That already we discussed for FCC, BCC and simple cubic. You remember all those things. Okay, so Z is the particles per number of particles per unit cell, and M is the mass of each particle, Na is the Avogadro number. So that is the mass of the unit cell. Then divided by volume of the unit cell. What is volume? A cube. I already told you. So Zm by Na divided by A cube, that is equal to Zm by A cube Na, where Z is the number of particles per unit cell, mass of each particle, A cube is the volume of the unit cell, Na is the Avogadro number. So using these equation we can calculate the density of the unit cell. So from this equation we have total 5 parameters. Knowing any 4 parameters we can calculate the 5th one. So this is a very important expression. Usually the problems are asking based on this equation. Okay, so you should thorough with the equation, and you keep in mind that density of the unit cell is same as that of density of the crystal. Now we only calculated the density of the unit cell. So how will you calculate the density of crystal? That is, crystal is made up of the arrangement of infinite number of unit cell. You know that because unit cell is the basic unit of the crystal, right? Okay, so number of unit cell repeated to get the crystal. So if we get the density of the unit cell means that is the density of the crystal also. Okay. So, you know the value of Avogadro number. Okay. By X-ray diffraction studies, we will get the density of the crystal or edge length of the crystal, and also by knowing this or any of the 4 factors, we can calculate the density using this equation. Now, we will do some problems based on this equation. Okay. Now, look at this problem. An element crystallizes in BCC lattice with an edge length 500 picometer. The density of the crystal they are given, that is 7.5 gram per centimeter cube. They are asking the question, how many atoms are present in 300 gram of the element. Okay. So, by using the density equation we can solve this. Okay. So, you know what is the density equation, that is Zm divided by A cube into Na. Then first, whenever they ask how many atoms, whenever they ask the questions like how many atoms are present, first you have to calculate the mass. Okay. So, Zm by A cube Na means you have to calculate the mass, molecular mass of the unit cell, that is capital M you have to calculate. That is given by density into A cube into Avogadro number divided by Z. You know, here they told that BCC lattice. BCC lattice, you know, the number of particles per unit cell is equal to 2. We already find out that. So, here density is equal to 7.5 gram per centimeter cube. Okay. So, mass you will get in gram unit because the density is given by gram centimeter cube. So, what will happen here? The edge length also you have to taken in centimeter. Here they are given with a unit picometer. So, edge length A is equal to 500 picometer. So, you have to convert this picometer into centimeter. So, how many centimeter? 500 into 10 raised to minus 10 centimeter. So, unit conversion you know. Okay. So, 500 into 1 picometer is equal to 10 raised to minus 10 centimeter. Meter lanengile 10 raised to minus 12 meter. So, here 500 into 10 raised to minus 10 centimeter. Why I am taking in centimeter unit? Because the density is given in the unit of gram per centimeter cube. If this is given in gram per meter cube means I have to take this in meter. Here it is in centimeter cube. That is why I am taking in centimeter. Okay. Okay. Then density into A cube into Avogadro number divided by Z. In BCC structure, Z value is equal to 2. So, simply you write that values, that is 7.5 into A cube means 500 into 10 raised to minus 10 whole cube into Avogadro number value you know 6.023 into 10 raised to 23 divided by 2. Okay. So, by solving this we will get 282.28 gram. This is a mass, so we will get in the unit gram. Okay. Now, what we have to calculate the how many atoms are present in 300 gram of the element. Okay. So, whenever they ask the number of atoms in this much amount of element means they are given in 300 gram number of atoms ആണ് നമുക്ക് കാണേണ്ടത് അല്ലേ. അപ്പോൾ 300 gram എത്ര ഗ്രാമിലുള്ള ആറ്റംസിൻ്റെ എലിമെൻ്റ് ആണോ കാണേണ്ടത് അത് ഡിവൈഡഡ് ബൈ നമുക്ക് നേരത്തെ കിട്ടിയ മോളിക്കുലർ മാസ് എത്രയായിരുന്നു 282.28. So, this one divided by 282.28 into Avogadro number. By solving this equation, you know value of Na, what is that? 6.023 into 10 raised to 23, Avogadro number itself. Okay. So, by solving all this, you will get 6.4 into 10 raised to 23. Much number of atoms are present in 300 gram of the element. So, this is the way you have to do the problems while they ask the number of elements. Okay. Otherwise, they can ask a problem like directly you have to find out the density. This is a little twisted problem, that is why I did here. Okay, one more problem we will do. Now, you look at this problem. KBr has a NaCl type structure. What is the distance between K plus and Br minus ion? And they are given the density also. What is that? 2.75 gram per centimeter cube. So, NaCl type structure means we know the structure is FCC structure. More correctly, we can call it as interpenetrating FCC. Okay, so FCC structure, you know, the particles are present at the corners and face center. Okay, so corner lundu, ella corners lundu, then all face centers lundu particles. So K plus and BR minus and തമ്മിലുള്ള ഡിസ്റ്റൻസ് ആണ് നമ്മളോട് ചോദിച്ചിരിക്കുന്നത്. അപ്പോൾ ഒരു കോർണറിലാണ് ഒരു അയോണും ഒരു അയോൺ അതിൻ്റെ ഫേസ് സെൻറ്ററിലാണെന്ന് വിചാരിക്കുക. അപ്പോൾ ഇതിൻ്റെ രണ്ടിൻ്റെ ഡിസ്റ്റൻസ് എന്ന് പറഞ്ഞാൽ എന്താ, internuclear distance, രണ്ട് പാർട്ടിക്കിളും the centers in the distance between the centers of the two particles. Okay, so this is the distance we have to find out. Actually, what is that? You know, this distance, what is that? For a cube, all the distance is given by edge length. So this distance is A. So what about this? Obviously it is A by 2. So A by 2 we have to find out. That you should understand while reading the question. Okay, എന്താണ് നമ്മൾ കണ്ടുപിടിക്കേണ്ടത് നമുക്ക് മനസ്സിലാവണം. ഓക്കെ, അപ്പോൾ they ask the question like what is the distance between K plus and Br minus. So where is K plus, where is Br minus, that you have to thorough. Okay, that you have to understand. Okay, so by knowing this you will get that the distance between these two ions is given by nothing but A by 2. Okay, so first you have to find out A. So you know, density equation is equal to Zm divided by A cube into Na. Okay, so here A you have to find out. That means A cube is equal to what? A cube Zm divided by D into Na. Here FCC structure means what is Z? Z equal to 4. And what about the molecular mass? M means molecular mass. Here the molecule is KBr. So KBr ന്റെ molecular mass നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റും. So KBr ന്റെ molecular mass എത്രയാ? 119 ആണ് വരിക. പൊട്ടാസ്യത്തിൻ്റെ BR-ൻ്റെ ഒക്കെ molecular mass നിങ്ങൾക്ക് അറിയാം. അത് രണ്ടും കൂട്ടുമ്പോൾ നമുക്ക് KBr ന്റെ molecular mass equal to 119. Okay, so that is equal to 4 into 119 divided by here 2.75 into 6.023 into 10 raised to 23. So by solving this mathematical equation you will get 6.6 into 10 raised to minus 8. എത്ര എന്തായിരിക്കും? Here density is given in gram per centimeter cube. Okay, so this is equal to 3 centimeter. So this is A. Now you have to find out the distance between K plus and Br minus ion, that is A by 2. So A by 2 is equal to 6.6 into 10 raised to minus 8 divided by 2. So that is equal to 3.3 into 10 raised to minus 8 centimeter. So ഇത്രയും ആയിരിക്കും അവ തമ്മിലുള്ള distance. So this is the way you have to do this. Okay, clear? Okay, now look at this problem. This is the same problem that is in your textbook. Okay, so this type of problem we already done. So an element has a body centered structure with an edge length of 288 picometer and density is given, that is 7.2 gram per centimeter cube. So they ask how many atoms are present in 208 gram of the element. Okay, so this is the same equation. Density, you know what is the equation? Zm by A cube into Avogadro number. So mass you have to find out. അല്ലേ, നമ്മൾ ഇങ്ങനെ ക്വസ്റ്റ്യൻ ചോദിച്ചാൽ ഏതാ ഫസ്റ്റ് കണ്ടെത്തേണ്ടത്? മാസ്. അപ്പോൾ മാസ് is equal to density into A cube into Na divided by Z. So simply you putting these values you will get an answer. ആ ആൻസർ ആയിരിക്കും നമ്മൾ അത്രയായിരിക്കും ഇതിൻ്റെ മാസ്. ഇനി എന്താ ചെയ്യേണ്ടത്? നമ്പർ ഓഫ് ആറ്റംസ് ഇൻ 208 ഗ്രാമിൽ എത്ര ആറ്റംസ് ഉണ്ടെന്ന്. അപ്പോൾ എത്ര ഗ്രാമാണോ തന്നത് അത് ഡിവൈഡഡ് ബൈ നമുക്ക് നേരത്തെ കിട്ടിയ മാസിൻ്റെ വാല്യൂ ഇൻറ്റു അവഗോഡ്രോ നമ്പർ. ഓക്കെ, സോ നമ്മൾ സിംപ്ലിഫൈ ചെയ്യുമ്പോൾ യു വിൽ ഗെറ്റ് ദ വാല്യൂ. ഓക്കെ, ദിസ് ഇസ് ദ വേ യു ഹാവ് ടു ഡൺ. സോ നമ്മൾ മുന്നേ ഇതേപോലെ ഒരെണ്ണം ചെയ്തതുകൊണ്ട് ഈ ഒരു പ്രോബ്ലം നിങ്ങൾ വീട്ടിൽ നിന്ന് വർക്കൗട്ട് ചെയ്യാം. ഓക്കെ, നെക്സ്റ്റ് ഇസ് the thallium crystallizes in either simple cubic or face centered cubic lattice of thallium plus and Cl minus ions. Then they are given the density, that is 9 gram per centimeter cube, and also the edge length are they given. Then what is they asked? What is the geometry of the crystal? So then how will you find out? You have to use the same equation, that is density is equal to Zm divided by A cube Na. Here what you have to find out? Z. after getting Z only, we have to identify which geometry of the crystal is. Okay. So, first of all, if they ask geometry, you have to concentrate on Z. Okay. All other values are given. Thallium chloride they given. So, thallium chloride molecular mass you have to calculate, and then what is the equation of Z? D into A cube into Na divided by M, molecular mass. Density തന്നിട്ടുണ്ട്, edge length നമ്മൾ ഇവിടെ സെൻറ്റിമീറ്ററിൽ തന്നെയാണ് തന്നത്. സോ ദർ ഇസ് നോ കൺവേർഷൻ ഈസ് നീഡഡ്. ദെൻ അവോഗാഡ്രോ നമ്പർ, ദെൻ മാസ്. ഇത്രയും കാൽക്കുലേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ നിങ്ങൾക്ക് ഒരു വാല്യൂ കിട്ടും. സപ്പോസ് 1 ആണ് കിട്ടിയെന്ന് വിചാരിക്കാം. ദെൻ വാട്ട് യു വിൽ കൺക്ലൂഡ്? ദാറ്റ് ഈസ് ദ ക്രിസ്റ്റൽ ഈസ് in simple cubic structure. If you are getting 4 means, what do you conclude? Yes, the crystal is in FCC structure. So, like the way you have to do when they ask a question like, what is the geometry of the crystal? Okay. So, I am not going to do this value and putting the value and calculation. You have to do in your home. Okay. So, this is the way you have to do the problem. This is very simple problem. We already done 3 problems. Okay. We are going for a new topic in solid state, which is that is imperfections in solids. Imperfections means crystal defects. So, what is defects? Why these defects occur? So, you know, when crystallization occurs in very fast or moderate rate, there occurs many imperfections in crystals. Okay, when the single crystal is formed only when the crystallization takes place at extremely slow rate. നിങ്ങൾ ലാബിലൊക്കെ ചെയ്യുമ്പോൾ ക്രിസ്റ്റലൈസ് ചെയ്യുമ്പോൾ നിങ്ങളോട് ടീച്ചേഴ്സൊക്കെ പറഞ്ഞിട്ടുണ്ടാവും, ക്രിസ്റ്റലൈസ് ചെയ്യുമ്പോൾ നമ്മൾ റിയാക്ഷൻ എന്താക്കിയാൽ മാറ്റും? സ്ലോലിയാണ് നമ്മൾ സോൾവെൻ്റൊക്കെ ആഡ് ചെയ്യുക അല്ലേ? സ്ലോലി ക്രിസ്റ്റലൈസ് ചെയ്താലാണ് നമുക്ക് എന്ത് കിട്ടുക? പെർഫെക്റ്റ് ക്രിസ്റ്റൽ കിട്ടുക. നമ്മളോട് പറയുന്നത് കേട്ടിട്ടുണ്ടാവും അല്ലേ? സോ ജനറലി സിംഗിൾ ക്രിസ്റ്റൽ ഈസ് ഒബ്റ്റൈൻഡ് ബൈ the crystallization occurs at extremely very slow rate. അങ്ങനെ ആവുമ്പോഴാണ് നമുക്കൊരു പെർഫെക്റ്റ് അല്ലെങ്കിൽ സിംഗിൾ ക്രിസ്റ്റൽ കിട്ടുന്നത്. സോ ക്രിസ്റ്റൽസിൽ നമുക്ക് ജനറലി കാണാവുന്ന ഒരു ഫിനോമിനനാണ് imperfections or defects. So, which are the types of defects and what are the reason for these defects and what is the after effects of this type of defects? So, we will discuss that, okay, in this class. Okay, so listen here. So, this what is called defects means basic irregularities in the arrangement of particles. That is, irregularities in the arrangement of constituent particles, we can call it as the term defects. And these defects or imperfections are broadly classified into 2 types. Which are they? Point defects and line defects. So, in your syllabus you have to study more about point defects. Okay. So, point defects, what is that? That is irregularities or deviations from ideal arrangement around a point or an atom in the crystals. So, irregularities around a point മാത്രമാണെങ്കിൽ അതിനെ നമ്മൾ എന്ത് പറയും? Point defects. Irregularities around a point or an atom in the crystal. Then it is called point defects. Okay. The next type is line defects. അപ്പോൾ എന്തായിരിക്കും line defects? Irregularities in the ideal arrangements around a entire row. അങ്ങനെയാണ് entire row of the lattice points. That type of defect is known as line defects. Okay, so I told you in your syllabus you have to study only about the point defects. So we are confined our next explanation with the point defects only. Okay, so now we will go detail about the point defects. So we can confine our discussion to point defects only. Okay. So point defects are classified into 3 types, which are the stoichiometric defects, impurity defects and non-stoichiometric defects. So first we will discuss about stoichiometric defect. So as the name indicates, in stoichiometric defects means that do not disturb the entire stoichiometry of the crystal. Okay. So in this type we have first one, vacancy defects. Stoichiometric defects means which do not disturb the stoichiometry of the crystal. This is otherwise known as intrinsic defects. intrinsic defect or thermodynamic defect അങ്ങനെയൊക്കെ പറയാം. So first one in this type, first one is vacancy defect, which means we have lots of particles in our unit cell, right? So first one is vacancy defect. What is vacancy defect? Any one of the particle or ഏതെങ്കിലും ഒരു പാർട്ടിക്കിൾസ് ഒക്കെ വാക്കൻ്റ് ആയിരിക്കും ക്രിസ്റ്റലിൽ. ക്രിസ്റ്റൽ ലാറ്റിസ് നമ്മൾ എടുത്തു കഴിഞ്ഞാൽ ഏതെങ്കിലും പ്ലേസസ് വാക്കൻ്റ് ആണെങ്കിൽ ദാറ്റ് ടൈപ്പ് ഓഫ് ഡിഫക്റ്റ് ഈസ് കോൾഡ് vacancy defect. What is the after effect of this defect? This site is vacant, right? Here also it is vacant. So this type of defect is called vacancy defect. In vacancy defects, normally the density of the crystal decreases. Why it is so? So you know the mass will be decreasing. Density means mass by volume. So whenever decrease in mass happens, the density also decreases. So in a vacancy defect, there is a decrease in density. Decrease in density. Okay, this type of defects generally shown by non-ionic solids. Non-ionic solids ആണ് the defects mainly show ചെയ്യുന്നത്. Okay, and the second type is interstitial defects. Here the particles, as you can see in the picture, the particles are occupied at the interstitial sites. So what will happen? The overall density of the crystal increases. So as you can see, the molecule number of atom particles increases, so that the mass also increases. So in this type of defects, the overall density of the system increases. So this is happen when the solid is heating, when the solid is getting heated. So this defects also shown by non-ionic solids. Okay, so in stoichiometric defects we have vacancy defect, then second one is interstitial defects. In vacancy defects the density decreases, but in interstitial defects the density increases. Okay, okay. Then next is third type, which is that Frenkel defects. In Frenkel defects, these type of defects are shown by solids, ionic solids, ionic solid. Earlier two are shown by non-ionic solid. Okay, here it is shown by ionic solids. Okay, so in this defects generally shown by generally cations of the small size ions and anions large size അങ്ങനെയാണല്ലോ ഉണ്ടാവുക. Okay, so in this type of defect generally cations are lower in size, anions are larger in size. Okay, so cations generally dislocate from their interstitial site, their respective sites, and jump into the interstitial sites. That is happening in Frenkel defect. So overall stoichiometry of the compound remains as same. Stoichiometry ne ഇത് effect ചെയ്യില്ല, but what will happen? അതിൻ്റെ correct site നിന്ന് dislocation സംഭവിക്കും. ആർക്ക്? കാറ്റിയോൺസിൻ്റെ ഡിസ്ലൊക്കേഷൻ സംഭവിച്ച് അത് ഇൻഡസ്ട്രീഷ്യൽ സൈറ്റിൽ വന്ന് ഓക്യുപ്പൈ ചെയ്യും. സോ ദിസ് ടൈപ്സ് ഓഫ് ഡിഫക്ട്സ് ജനറലി ഷോൺ ബൈ കാറ്റിയോൺസും ആനിയോൺസും തമ്മിൽ ലാർജ് ഡിഫറൻസ്, സൈസിൽ നല്ല ഡിഫറൻസ് ഉള്ള അത്തരം സോളിഡ്സ് ആണ്. കാറ്റിയോൺസ് ആൻഡ് ആനിയോൺസ് ഹാവ് ലാർജ് സൈസ് ഡിഫറൻസ്. അങ്ങനെയുള്ള ഒരു സോളിഡ്സ് ആണ് ദിസ് ടൈപ്പ് ഓഫ് ഡിഫക്ട്സ് ജനറലി ഷോ ചെയ്യുന്നത്. സോ ഫോർ എക്സാമ്പിൾ Zn as AgCl, AgBr, AgI, etc. shown by this type of Frenkel defect. Okay, so you know in a small size of the cation of Ag plus Zn2 plus. Okay, this defect are generally shown by the solids of the type there is a large difference between the size of cation and anion. So that's all about the Frenkel defect. In Frenkel defects it is seen that there is no change in the density. Okay, നേരത്തെ നമ്മൾ പറഞ്ഞിരുന്നു ഡെൻസിറ്റി കൂടുകയും കുറേയൊക്കെ ചെയ്യുന്നുണ്ടായിരുന്നു ഓരോ ഡിഫക്റ്റിലും. ബട്ട് ഇൻ Frenkel defect there is no change in the density. Next is fourth type, that is called Schottky defect. Here what will happen? Here also there is no change in the stoichiometry of the compound. Here both cation and anion are missing, and the missing number of cation and anion will be equal. Here you look here, one positive ion is missing and also one negative ion is missing here. So the missing number of both cation and anion will be equal. equal number. So which does not affect the overall stoichiometry of the compound. So what will happen, the density here, this is like that of the vacancy defect. So here also the density decreases. Okay. So density of the crystal decreases here. Then next type is impurity defects. And in non-stoichiometric defects second type point defects we studied 3 types of defects are there, which are the stoichiometric defects, impurity defect and non-stoichiometric. Stoichiometric defects we discussed, which are the vacancy defect, interstitial defects, then Frankel defects, Schottky defects. Next is second type of point defects is impurity defects. What we call impurity defect. So in impurity defects, when suppose you take the case of NaCl, when NaCl crystallizes, there occurs the crystallization of strontium chloride also. SrCl2 also, some amount of SrCl2 also crystallizes there. Okay, so you look at this. Suppose here we have Na plus and Cl minus ions. So suppose Na plus, Cl minus, Na plus, Cl minus, like that ions you can see in here, Cl minus, Na plus, Cl minus. So any of the Cl minus Na plus ion എടുത്ത് ഏതെങ്കിലും ഒരു Na plus ion സ്ഥാനത്ത് ആര് പോയി crystallize ചെയ്യും, Sr2 plus. Okay, strontium 2 plus. So ഒരു strontium 2 plus replace ചെയ്യും, ഒരു strontium 2 plus രണ്ട് Na plus ions replace ചെയ്യും. So here SrCl2 crystallizes as an impurity in NaCl. അപ്പോൾ എന്താ സംഭവിക്കുക, here 1 Na plus ന്റെ സ്ഥാനത്ത് ആര് വരും, Sr2 plus. ഒരു Sr2 plus ഓക്യുപ്പൈ ചെയ്യണമെങ്കിൽ രണ്ട് Na plus എന്താക്കണം, വാക്കൻ്റ് ആക്കണം. സോ രണ്ട് Na plus വാക്കൻ്റ്, ഒരു Na plus ന്റെ വാക്കൻസിയിൽ who will fill Sr2 plus and one vacant site is remain as such. So number of vacant site will be equal to the number of Sr2 plus ion in the crystal structure. So this type of defects is called impurity defects. Okay. So one more example for impurity defect is shown by the solution of AgCl and CdCl2. Okay. So next we will move to next type, non-stoichiometric defect. The third type of point defect is non-stoichiometric defect. So here also we have 2 types, metal excess defect and metal deficiency defects. First we will look at what is metal excess defects. So here the excess is cation. For example, when NaCl crystal is heating NaCl crystal, what will happen? Sodium escape into on the surface. Sodium metal is move into the surface of the crystal. Okay, and chloride ion also move into the surface. The sodium and chloride ion combines. When sodium combine with chloride ion means that obviously sodium ions, so Na plus, so sodium metal releases one electron for forming NaCl, right? So what will happen, when on heating sodium chloride, sodium atom move on to the surface of the crystal, and also the chloride ions also move to the surface. Then there appears a vacant site, vacant anionic site. Chloride ion ഇവിടുന്ന് പോയി കഴിഞ്ഞ് സർഫസിലേക്ക് പോയി അവിടെ ഒരു vacant site ഉണ്ട്, ഒരു anion vacant ആയിരിക്കും. And what will happen on the surface? The sodium combine with this Cl minus ion. So when sodium combine with the Cl minus means there is a release of electron. That electrons come and occupy the anion vacant site. So that is avada anion chloride ion poyittulla vacant site il are occupy that electron. So electron will occupy at the vacancy created by the anion. There occurs a more Na oru chlorine vacant aanengil oru Na plus more ആയിട്ട് ഫോം ചെയ്തിട്ടുണ്ട്. സോ ആനിയോൺ, ദാറ്റ് ഈസ് ആനിയോൺ ഡെഫിഷ്യൻസി ആണ് ഇവിടെ, ബട്ട് കാറ്റയോൺ എക്സസ് ആണ്. സോ ദിസ് ടൈപ്പ് ഓഫ് ഡിഫക്റ്റ് ഈസ് നോൺ ആസ് മെറ്റൽ എക്സസ് ഡിഫക്റ്റ്. So overall stoichiometry of the compound is not maintained here, right? Or anion vacant aanu oru cation excess aanu. So this type of defects is called metal excess defect. So one important property is there here, that is the anion vacancy is filled by the electron produced from Na plus, right, sodium ions. So this electron ingane capture ചെയ്തിട്ട് ഈ സെന്ററിനെ നമ്മൾ ഒരു പ്രത്യേക പേര് പറയും, that is called F center. German name Farben center for color center എന്നാണ് ഇതിൻ്റെ പേര്. That is what we call it as F center. ഈ F centersൽ electrons ഉണ്ട്. Electrons acquire energy from visible light and it imparts certain colors to the crystal. So that is why it is called F center. And NaCl is yellow in color when it is heating. That is due to this effect. That is this electron, F centers electrons absorb energy from visible light and it imparts certain colors to the crystal. So sodium chloride is yellow in color when it is heated. Then also lithium chloride, it imparts pink color. And you look at KCl, it gives violet color or lilac color. Then zinc oxide, ZnO. ZnO at room temperature which is white in color, when it is heated what will happen? Zn heating, it will give Zn 2 plus ion, then half O2 plus 2 electron, right. So electron avada produce cheyum, then F centers produces, then it is become yellow in color on heating. At room temperature it is white color, but on heating it is what is the color? Yellow in color. Okay. The next type is metal deficiency defect. Okay. So metal deficiency defect, metal deficiency defect. This defect is shown by generally FeO, iron oxide. So in metal deficiency defects, most of there are certain compounds which are occurring, it is very difficult to create in stoichiometric ratio, stoichiometric composition. Okay, so one of the typical example is FeO. Okay, in FeO compound generally Fe ranging from 0.93 to 0.96. There is a difficulty for preparing the stoichiometric ratio. So this is one of the example for metal deficiency defect. Here what will happen? The Fe2 plus cation is missing and Fe3 plus ഒരു Fe2 plus miss ചെയ്തിട്ട് അടുത്ത സൈറ്റിൽ ഒരു Fe3 plus ആയിരിക്കും present ആവുക. Certain type of defect is, such type of defect is called metal deficiency defects, usually shown by FeO. Okay. So in today's class we discussed all about the imperfections in crystal, mainly about point defects. So because we have to study the point defects only in your syllabus. So you all, I hope you all understand all those things, and among these very important thing is that F center and color center. So they will ask question like what is the color of such crystals, like that the question they will ask. So in next class we will discuss more about the electrical properties of solids. Okay, thank you.